The primary objective of this simulation is to analyze the unsteady aerodynamic behavior of the aircraft under different oscillation modes, including yaw, pitch, and roll. A detailed transient CFD analysis was performed to capture the time-dependent flow phenomena and accurately compute the aerodynamic responses. The obtained results were used to extract 24 dynamic derivative coefficients, which describe the aircraft's unsteady stability characteristics. These coefficients and their corresponding diagrams provide valuable insights into the vehicle's dynamic performance and stability behavior. As you can see here, this geometry is the subject of our discussion in this simulation. For this geometry, we have created a cylindrical domain with a hemispherical cap. Moreover, inside this domain, as you can observe, there is a spherical domain that completely surrounds the drone geometry. This spherical domain is of particular importance to us because, in this simulation, the oscillations will be applied to this spherical zone using a UDF code. In this section, you can see the mesh generated for this geometry. In the regions close to the geometry, the mesh is finer and denser in order to capture the physical phenomena more accurately. This mesh is a hybrid type, and the boundary layer has been captured in this mesh. The view you see here represents a cross-sectional cut of the geometry from one side. In the Fluent settings of this simulation, it should be noted that a pressure-based solver with absolute velocity formulation and transient time setting has been used. Since the Mach number of the flow is 0.6, it is appropriate to use the pressure-based solver for this simulation, provided that the fluid density is defined as an ideal gas. To achieve a more accurate simulation of the flow behavior in this regime, the K-omega SST turbulence model has been employed in this simulation. In the Cell Zone Conditions section under Slide Fluid Zone, the corresponding UDF file was selected. This file is the same code defined in the Mesh Motion section and is used here to apply the mesh motion and oscillations to the fluid zone. Here, you can see the various boundary conditions of the problem, categorized according to their zone types. These include the inlet, interface, internal zones, and walls. In the initialize section of the problem, as you can see, we use the standard initialization method to initialize the flow field. In the Run Calculation section, for the transient simulation, we use 3,000 time steps with a time step size of 0.01 seconds. These settings cover a total of 30 seconds of the simulation process. These are the results for the yaw oscillations, along with the corresponding derivative diagrams. Similarly, for the pitching and rolling oscillations, the derivative coefficients and diagrams have also been extracted. After the comprehensive transient CFD simulations, the necessary time-accurate data were successfully generated to determine the complete set of 24 dynamic derivative coefficients for the aircraft. These critical parameters, representing the aircraft's unsteady stability characteristics, were extracted and precisely tabulated. Corresponding graphs were also plotted to visually illustrate their correlation with the oscillation parameters. I hope this video was useful for you. To benefit from Mr. CFD services, including simulation, consultation, and training, visit our website and contact us via these addresses.